Space has always captured humanity's collective imagination. Among the pantheon of celestial bodies that have fascinated us, Jupiter stands out as the largest planet in our solar system. Its vibrant stripes and prominent great red spot make it easily recognizable. However, there's much more to Jupiter than its size and famous storm. Our knowledge has grown exponentially with advancements in space technology and exploration. Jupiter is a gas giant composed mostly of hydrogen and helium. Its diameter is approximately 11 times that of Earth, and it's so large that over 1,300 Earths could fit inside it. Despite its size, Jupiter has the shortest day of all the planets, rotating on its axis every 9.9 hours. Jupiter's magnetic field is the strongest of any planet in the solar system, created by electrical currents driven by its fast rotation and the movement of metallic hydrogen within its outer core. Jupiter's famous bands are actually high-pressure zones, characterized by lighter-colored clouds, while its darker regions are low-pressure zones. The vibrant colors we see are due to different types of clouds. Ammonia crystals create the white bands, while other chemicals produce the reddish, brownish, and yellowish hues. As for the Great Red Spot, this iconic feature is a persistent high-pressure region in the atmosphere, resulting in a storm that has been ongoing for at least 300 years. The Great Red Spot is one of the most recognizable features of Jupiter, the largest planet in our solar system. At its widest point, it stretches 1.3 times the diameter of Earth, although its size varies over time. Notably, it has been shrinking in recent decades. The storm has been continuously observed since the late 19th century, but historical records suggest its existence for at least 300 years. The Great Red Spot is located in Jupiter's southern hemisphere, nestled within a westward-moving jet stream called the South Equatorial Belt. The red color of the Great Red Spot is still a subject of research. It is thought that the color may come from complex organic molecules, red phosphorus, or possibly compounds containing sulfur, but the exact chemical reactions that give the spot its vivid color remain a mystery. The storm rotates counterclockwise with a period of about 6 days. Interestingly, the rotation speed, size, and color of the spot can change, reflecting the storm's complex interaction with its surroundings. The longevity of the Great Red Spot is intriguing. While storms on Earth last for days or weeks at most, the Great Red Spot has persisted for centuries. This longevity is likely due to Jupiter's rapid rotation and lack of a solid surface, which minimizes the frictional dissipation of the storm's energy. The Great Red Spot offers a window into the atmospheric dynamics of Jupiter, a gas giant with conditions vastly different from those of our home planet. Understanding the atmospheric dynamics of Jupiter, a gas giant with conditions vastly different from our home planet, not only unravels the secrets of Jupiter but also sheds light on the broader principles governing atmospheres, including our own. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each of these moons is a world unto itself. Io is the most volcanically active body in the solar system, its surface covered in sulfur and sulfur dioxide, giving it a colorful, mottled appearance. Europa has a crust of ice, and scientists believe it might harbor a subsurface ocean, making it a potential site for extraterrestrial life. Ganymede, the largest moon in the solar system, is the only moon known to have its own magnetic field. Callisto, characterized by its extremely cratered surface, is also believed to have an ocean beneath its surface. Jupiter was known to have 79 moons, but additional moons may have been discovered since then. Saturn isn't the only planet with a ring system, although much fainter and smaller. Jupiter also has rings, composed mainly of dust particles from impacts on the planet's small innermost moons. These rings were first discovered by NASA's Voyager 1 spacecraft in 1979. The study of Jupiter has come a long way since Galileo's first observations. Multiple missions, such as Pioneer 10 and 11, Voyager 1 and 2, Galileo, Juno, and more, have been sent to Jupiter to study its composition, magnetic field, and moons. Pioneer 10 and 11 were the first spacecraft to make a close approach to Jupiter, providing valuable data about its radiation belts, magnetic field, and some moons. Voyager 1 and 2 made significant discoveries, such as detecting Jupiter's rings and confirming Io's volcanic activity. The Galileo orbiter spent 8 years studying the planet and its moons, and the attached probe made a direct plunge into Jupiter's atmosphere, providing the first direct measurements of its composition. The Juno mission, still ongoing as of 2021, has made significant contributions to our understanding of Jupiter's internal structure, atmosphere, and magnetosphere. Jupiter, the colossal gas giant, remains a focal point of curiosity for astronomers and space enthusiasts alike. Its impressive size, complex atmospheric dynamics, multitude of moons, and faint ring system make it a fascinating object of study. As we continue to explore Jupiter through telescopic observations and space missions, we unravel the secrets it holds, enriching our understanding of the cosmos. For now, we marvel at the celestial symphony Jupiter conducts, its presence a testament to the intricate, diverse, and vast nature of our solar system. Venus is nearly identical to Earth in size, making it one of our most similar neighbors in the solar system. With a mean radius of about 3,760 miles, it's approximately 95% the size of Earth. Its mass is about 81.5% that of Earth. This similarity in mass and size means that Venus also has a comparable density to Earth, approximately 5.24 g per cubic cm, implying a similar rock-iron composition. Venus and Earth have a comparable structure, a central iron core surrounded by a rocky mantle and a thin crust. The core of Venus, while not as well understood as that of Earth, is believed to be partially liquid, similar to Earth's. This iron core is estimated to be about 2,000 miles in diameter. Above the core lies Venus's mantle, composed of silicate rock that extends up to approximately 1,550 miles from the planet's center. This is overlaid by a thin crust, estimated to be 6 to 12 miles thick. The rotation of Venus is a unique characteristic among the planets of our solar system. Unlike most other planets, which spin on their axis in the same direction that they orbit the Sun, Venus rotates in the opposite direction. This is a phenomenon that isn't yet fully understood by scientists, but some believe it may be due to a massive collision with a celestial body in the past, which altered the planet's rotational dynamics. Venus rotates extremely slowly, with a sidereal day taking 243 Earth days, the slowest rotation of any planet in the solar system. This slow rotation contributes to the planet's lack of a significant magnetic field. Another quirk of Venus's rotation is that a solar day on Venus, the time from one sunrise to the next, is shorter than its sidereal day. Due to its retrograde rotation and orbit around the Sun, the solar day on Venus is about 116.75 Earth days. The planet's year, or the time it takes to orbit the Sun, is about 225 Earth days, which is shorter than its sidereal day. This makes Venus one of the few planets where a day is longer than a year. The surface gravity on Venus is about 90% of the surface gravity on Earth, meaning that if you were able to stand on Venus, you would feel slightly lighter than on Earth. However, the extreme atmospheric pressure and temperature would make it impossible for humans to survive without protection. Venus's surface appears to be geologically young, with a relatively low number of craters, indicating a surface age between 300 million and 600 million years old. Scientists believe that Venus undergoes a cyclical process where heat from the planet's interior causes the surface to be repaved in a global resurfacing event. There is strong evidence of widespread volcanic activity on Venus. Thousands of volcanoes dot its surface, ranging from less than a mile in diameter to over 150 miles. The planet has far more volcanoes than any other in our solar system. However, there's currently no definitive evidence that these volcanoes are still active, although recent studies suggest that some may have erupted within the last few million years. Despite the apparent geological activity, Venus doesn't experience significant tectonic activity like Earth. While Venus does have mountain ranges and rift valleys similar to those seen in tectonically active regions on Earth, it lacks the kind of large, distinct tectonic plates seen on our home planet. This might be due to the planet's slow rotation, which limits the Coriolis effect necessary to drive large-scale tectonic activity. Venus's atmosphere is one of its most distinctive and intriguing characteristics. The atmosphere is primarily composed of carbon dioxide, with most of the remainder being nitrogen. However, there are also traces of other gases such as sulfur dioxide, water vapor, carbon monoxide, argon, and helium. This composition is vastly different from Earth's nitrogen-oxygen atmosphere, making Venus's air toxic to humans and most known forms of life. The atmosphere of Venus is arranged in several layers: the troposphere, extending from the surface to about 40 miles up, the mesosphere, stretching from the top of the troposphere to about 56 miles high, and the thermosphere, which reaches up to 125 miles above the planet's surface. Above this, there's a transitional region called the exosphere, which merges with the void of space. The high concentration of carbon dioxide in Venus's atmosphere creates a strong greenhouse effect, trapping heat and making it the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. The greenhouse gases in the atmosphere absorb heat energy radiated from the Sun, preventing it from escaping back into space. This results in surface temperatures averaging around 467 degrees Celsius, which is hot enough to melt lead. There's very little temperature variation between day and night or between the equator and the poles due to the thick atmosphere's efficient heat distribution. This results in a virtually constant furnace-like temperature all over the planet's surface. The atmospheric pressure on Venus is enormous, approximately 92 times greater than Earth's at sea level. This is equivalent to the pressure experienced 0.62 miles deep in Earth's oceans. A human exposed to such pressure without protection would be crushed. Despite this, high up in Venus's atmosphere, approximately 31 miles above the surface, the pressure and temperature conditions are similar to those on Earth's surface. Venus's atmosphere is perpetually cloaked in thick, opaque clouds that cover the entire planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus is so bright and easily visible from Earth. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few mph. Venus boasts the highest mountain in the solar system, Maxwell Montes, rising 20 kilometers above Venus's mean surface level. The planet's surface is also marked by numerous impact craters, extensive lava flows, and unique surface features like coronae, circular structures caused by the upwelling of hot material from the mantle, and arachnoids, circular formations with complex fracture patterns. Due to Venus's slow rotation and dense atmosphere, the planet doesn't experience significant seismic activity like Earth. However, recent studies suggest that Venus may still be geologically active. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all significantly contributed to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet and the first successful landing on another planet. These missions provided valuable data on Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus using radar to penetrate the thick cloud cover. This mission revealed details about Venus's surface features and geology. Despite the challenges posed by Venus's harsh conditions, scientists remain interested in further exploration of the planet. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns. Venus, our neighboring planet, is an intriguing world of extremes. Its harsh environment poses significant challenges to exploration, yet its similarity to Earth in size and composition, along with hints of potential past water and geologic activity, keeps our curiosity alive. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of the solar system and our place in it. As a reflection on our own planet's potential future, Venus serves as both a warning and an opportunity for scientific discovery. Aliens, are they real? Do they exist? Aliens, are they real? Do they exist? And if so, what do they look like? Today we will dive deep into the topic of aliens, exploring various theories and facts about these mysterious creatures. Extraterrestrial life exists. This theory suggests that life exists elsewhere in the universe, perhaps even within our own solar system. Microbial life could potentially exist on Mars or some of the moons of Jupiter and Saturn, for example. More complex life forms, such as intelligent civilizations, could also exist on planets orbiting other stars. The Fermi paradox. The Fermi paradox asks, if intelligent life is common in the universe, why haven't we detected any evidence of it? Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that they are too far away or have no desire to communicate with us. Ancient aliens. This theory suggests that aliens have visited Earth in the past and influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings, unidentified flying objects, are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, some remain unexplained and could potentially be evidence of extraterrestrial visitation. The simulation theory. This theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. To start, let's address the most basic question: do aliens exist? According to the Drake equation, developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. So, let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in a Goldilocks zone, not too hot, not too cold, and with the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways that we can't even comprehend. Their methods of communication might be vastly different from ours. So, what should we do if we ever encounter aliens? Many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species, or perhaps they are too far away to detect our signals, and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. Scientists have also found evidence of subsurface oceans on some of Jupiter's and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Venus's atmosphere is perpetually cloaked in thick, opaque clouds that cover the entire planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus is so bright and easily visible from Earth. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few mph. Venus boasts the highest mountain in the solar system, Maxwell Montes, rising 20 kilometers above Venus's mean surface level. The planet's surface is also marked by numerous impact craters, extensive lava flows, and unique surface features like coronae, circular structures caused by the upwelling of hot material from the mantle, and arachnoids, circular formations with complex fracture patterns. Due to Venus's slow rotation and dense atmosphere, the planet doesn't experience significant seismic activity like Earth. However, recent studies suggest that Venus may still be geologically active. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all significantly contributed to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet and the first successful landing on another planet. These missions provided valuable data on Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus using radar to penetrate the thick cloud cover. This mission revealed details about Venus's surface features and geology. Despite the challenges posed by Venus's harsh conditions, scientists remain interested in further exploration of the planet. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns. Venus, our neighboring planet, is an intriguing world of extremes. Its harsh environment poses significant challenges to exploration, yet its similarity to Earth in size and composition, along with hints of potential past water and geologic activity, keeps our curiosity alive. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of the solar system and our place in it. As a reflection on our own planet's potential future, Venus serves as both a warning and an opportunity for scientific discovery. Aliens, are they real? Do they exist? Aliens, are they real? Do they exist? And if so, what do they look like? Today we will dive deep into the topic of aliens, exploring various theories and facts about these mysterious creatures. Extraterrestrial life exists. This theory suggests that life exists elsewhere in the universe, perhaps even within our own solar system. Microbial life could potentially exist on Mars or some of the moons of Jupiter and Saturn, for example. More complex life forms, such as intelligent civilizations, could also exist on planets orbiting other stars. The Fermi paradox. The Fermi paradox asks, if intelligent life is common in the universe, why haven't we detected any evidence of it? Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that they are too far away or have no desire to communicate with us. Ancient aliens. This theory suggests that aliens have visited Earth in the past and influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings. Unidentified flying objects are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, some remain unexplained and could potentially be evidence of extraterrestrial visitation. The simulation theory. This theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. To start, let's address the most basic question: do aliens exist? According to the Drake equation, developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. So, let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in a Goldilocks zone, not too hot, not too cold, and with the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways that we can't even comprehend. Their methods of communication might be vastly different from ours. So, what should we do if we ever encounter aliens? Many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species, or perhaps they are too far away to detect our signals, and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. Scientists have also found evidence of subsurface oceans on some of Jupiter's and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact could be on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could also pose a threat if the aliens have hostile intentions towards us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, and so any speculation about their intentions or behaviors is purely hypothetical. Some people argue that aliens could be dangerous if they are more technologically advanced than us and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention to interact with us at all. Overall, while it's fun to speculate about the potential dangers of alien life, the truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. The search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. While the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself. At the outset, nothing existed. Then, the cosmos began to take shape some 13.7 billion years ago. How this came to be, or if there was ever a time before time, remains a mystery. Yet physicists have pieced together an approximate timeline of significant events in the cosmos's existence, using telescope data and models of particle physics. From its beginning to its inevitable demise, we will examine key points in the evolution of our universe. The Big Bang. The Big Bang is a moment in time, not a location in space, from which all else unfolded. To be more precise, it's the first second of time, the point in history from which all other seconds have been measured. Despite its common name, the Big Bang wasn't an explosion but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand that the laws of physics break down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. Next, the universe rapidly expanded in size. It may have expanded exponentially after the Big Bang, tearing apart previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. However, further investigation revealed that interplanetary dust was causing interference, not inflation. Quark-gluon plasma. Just a few milliseconds after the Big Bang, the temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit. During this time, quarks were free to move about. These quarks were combined with gluons, carriers of the strong nuclear force, in a primordial soup that pervaded the entire universe. Scientists have replicated these conditions in particle accelerators on Earth. However, these challenging conditions only lasted for a few fractions of a second. The early epoch. In the subsequent period of time, perhaps a few thousandths of a second after the Big Bang, the universe continued to expand and cool. This created an environment conducive to the merging of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms. Protons and neutrons fused together during the first 3 minutes of the universe's existence, creating an isotope of hydrogen known as deuterium, along with helium and a trace amount of the next lightest element, lithium. However, this process ceased as the temperature dropped. About 380,000 years after the Big Bang, hydrogen and helium atoms combined with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this era first identified in 1965, was created when photons, previously colliding with electrons, were able to move freely without being disrupted. The Dark Ages. There was a lengthy period during which nothing in the cosmos emitted any light. This time frame, around 100 million years after the Big Bang, is known as the Cosmic Dark Ages. Since astronomers gather much of their knowledge about the universe by studying starlight, this era remains exceptionally challenging to study. The first stars. The first stars formed when hydrogen and helium began to compress into massive spheres about 180 million years after the Big Bang, creating hellish temperatures at their centers. The universe entered a period known as cosmic dawn or reionization after the intense photons from these early stars and galaxies broke apart neutral hydrogen atoms into protons and electrons. Although it's difficult to pinpoint the exact duration of reionization, scientists estimate that it was completed around 500 million years after the Big Bang. Large-scale structures. Nearly a billion years after the Big Bang, supermassive black holes began forming at the centers of merging early galaxies. Intense quasars, visible from 12 billion light-years away, switched on and began emitting their bright beams of light, marking a significant era in the middle years of the universe. Throughout the subsequent few billion years, the cosmos underwent further evolution. Denser regions in the early universe drew in more material due to gravity, leading to the formation of a gorgeous filamentary cosmic web. These structures slowly expanded into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. About 4.5 billion years ago, a yellow star with rings formed from a cloud of gas in one galaxy. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. The third planet from the Sun, Earth, either retained much of its water during this process or received a deluge of ice and water from comets later on. Earth and humanity. Primitive bacteria appeared on this third watery world between 3.8 and 3.5 billion years ago. These organisms evolved over time into incredible marine creatures and enormous dinosaurs. Around 200,000 years ago, upright beings capable of contemplating the vastness of space and learning about the universe emerged. The end or not? This isn't the final chapter, of course. The future of the cosmos remains a mystery to physicists. It largely depends on our ability to accurately quantify the characteristics of dark energy, the unknown factor thought to be accelerating the expansion of the universe. If the universe continues expanding forever, all stars in all galaxies will eventually burn out, and even black holes will evaporate, leaving behind a lifeless cosmos filled with inert energy. Alternatively, the universe might face a great crunch, a reversal of the Big Bang, where gravity triumphs over the expansionary force of dark energy. Another possibility is the Great Rip, where the cosmos tears itself apart if dark energy accelerates the expansion to such a degree that everything drifts further and further apart. Determining the age of the universe. Scientists have spent decades studying the universe using various tools and techniques to unravel the mysteries of our cosmic past. Through their efforts, they have determined that the universe is estimated to be around 13.8 billion years old. The search for the age of the universe began in the early 20th century, when astronomers first realized that our universe was expanding. The concept of an expanding universe was first proposed by Belgian astronomer Georges Lemaitre in 1927. However, it wasn't until the work of American astronomer Edwin Hubble in the 1920s and 1930s that the idea gained widespread acceptance. Hubble's groundbreaking observations of distant galaxies revealed that they were moving away from us at great speeds. The farther away a galaxy was, the faster it moved. This relationship, known as Hubble's law, suggested that the universe was not static, but expanding. If the universe is expanding, it must have been smaller in the past. This realization led scientists to wonder just how old the universe was. Early attempts to estimate the age of the universe. The first attempts to estimate the universe's age were based on models of stellar evolution. Scientists knew that stars undergo predictable changes as they age. They believed that by studying the properties of stars in our own galaxy, they could determine the age of the universe. However, these early estimates were plagued by uncertainties in our understanding of stellar evolution and ranged from a few million years to several billion years. Breakthrough in the 1960s. In the 1960s, a more accurate method for determining the age of the universe was discovered. In 1964, astronomers Arno Penzias and Robert Wilson detected a faint background radiation present in all directions of the sky. This radiation, known as the cosmic microwave background, is thought to be the leftover radiation from the Big Bang, the event that marked the birth of the universe. The discovery of the cosmic microwave background was a major breakthrough in understanding the universe and provided scientists with a powerful tool for estimating the universe's age. By studying the properties of the cosmic microwave background, scientists could infer important details about the early universe, such as its temperature and composition. This information, in turn, could be used to estimate the age of the universe. Refining the estimate. Over the next few decades, scientists refined their measurements of the cosmic microwave background and improved their understanding of the early universe. They also developed more sophisticated models of cosmic evolution that took into account the effects of dark matter and dark energy, two mysterious substances that make up the majority of the universe. By combining these observations and models, scientists arrived at an estimate of 13.8 billion years for the age of the universe. Confirming the age of the universe. This estimate has been confirmed by a variety of independent measurements, including observations of distant supernovae and the large-scale structure of the universe. The age of the universe is one of the most well-established facts in cosmology. This fact holds profound implications for our understanding of the cosmos. The age of the universe reveals that our universe has a long and fascinating history stretching back billions of years to a time when it was just a tiny, hot, and dense singularity. It shows that the stars and galaxies we see today are the result of billions of years of cosmic evolution, driven by the forces of gravity and the interplay between matter and energy. At 13.8 billion years old, why is the universe still expanding at an accelerating rate? What is the nature of dark matter and dark energy, and how do they shape the evolution of the universe? How did the first stars and galaxies form, and what was the nature of the universe in its earliest moments? These are just a few of the many questions cosmologists are working to answer. The age of the universe provides a crucial piece of information in the quest to understand the cosmos, but it is just one part of a much larger puzzle. One of the most fascinating aspects of the age of the universe is how it connects to the fundamental nature of space and time. According to Einstein's theory of general relativity, space and time are intertwined, forming a four-dimensional fabric known as spacetime. This fabric can be warped and distorted by the presence of matter and energy, leading to phenomena like gravitational waves and black holes. The age of the universe tells us that spacetime has been evolving for billions of years, stretching and warping in response to cosmic forces. It shows that the very fabric of the universe has a history, and that the structures we see today are the result of an intricate interplay between spacetime, matter, and energy. While the universe is expanding at an accelerating rate today, it is still unclear what its ultimate fate will be. Some theories suggest the universe will continue to expand forever, eventually becoming a cold and dark place devoid of stars and galaxies. Other theories propose that the universe will eventually collapse in on itself, leading to another Big Bang and the birth of a new universe. Whatever the universe's ultimate fate may be, the age of the universe tells us that we are living in a remarkable moment in cosmic history. We have the opportunity to study the universe while it is still evolving and changing, with stars still being born and galaxies still colliding and merging. By studying the universe and its evolution, we can gain insights into the fundamental nature of the cosmos and our place within it. The age of the universe also offers insights into the likelihood of intelligent civilizations existing elsewhere in the cosmos. If life is a relatively common occurrence in the universe, and if the conditions for the development of intelligent life are present on other planets, there may be many civilizations out there that are much older and more advanced than our own. Furthermore, the age of the universe has implications for our search for extraterrestrial life. By studying the conditions that led to the emergence of life on Earth, and by exploring the diversity of life forms on our planet, we can gain insights into the types of environments that might support life elsewhere in the universe. Some theories even suggest that our universe is just one of many in a multiverse, a vast and complex network of parallel universes with their own unique properties and histories. The age of the universe suggests that if a multiverse does exist, then there has been ample time for the emergence of many different universes, each with its own unique history and destiny. Finally, the age of the universe reminds us of the incredible beauty and wonder of the cosmos. From the cosmic microwave background radiation left over from the Big Bang to the intricate dance of stars and galaxies across the night sky, the universe is a rich and complex tapestry of phenomena that is both awe-inspiring and humbling. In conclusion, the age of the universe is a remarkable fact that has profound implications for our understanding of the cosmos and our place within it. It provides insights into the origins and evolution of the universe, the potential for extraterrestrial life, the nature of reality itself, and the beauty and wonder of the cosmos. As we continue to explore the mysteries of the universe, the age of the universe will remain a key piece of information guiding us in our quest to understand the cosmos and our place within it. We once only knew about the planets that circled around our sun, but now we know that there are rocky worlds and huge gas clouds that orbit other stars. They have their own great stories to tell. The early history of these planets would have been incredibly violent. Planets are formed the same way everywhere. They emerge from dust and other materials left over after stars are born. So, if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. Our solar system has 8 planets, but now we know that they are just a small part of a vast family of planets in the sky. This is an important moment in the history of science, as we confirm the existence of other planetary systems out there. In our Milky Way galaxy alone, which contains 200 billion stars, there are probably dozens of planets. NASA launched the Kepler Space Telescope in 2009 on a 6-year mission to discover new planets orbiting other stars. So far, it has found more than 400 planets. Some are enormous gas giants, 5 times larger than Jupiter. Some follow wild, erratic orbits, so close to a star that they are burning up. One thing is clear, no 2 planets are the same. Each one is unique, but most of these new worlds are very far away and difficult to study. Most of what we know about how planets work comes from the 8 that orbit our sun. In our own solar system, planets come in 2 main types. The inner solar system has 4 rocky planets: Mercury, Venus, Earth, and Mars. The outer solar system contains 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, each planet began to develop its own unique characteristics. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the rocky planets closer to the sun and the gas giants farther away, came from this cloud of space debris. Although all the planets in our solar system are made from the same materials, they formed under very different conditions. Some formed close to the sun, where it was much hotter, while others formed farther away, where it was much colder. Since these environments were so different, the planets that emerged from them also turned out very different. At the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, methane, and other elements. These materials in the dust cloud are like ingredients in a cake. They cook in different ways depending on how the ingredients are mixed and how hot the oven is. Just like when you bake a cake, the ingredients change as they cook. This is essentially what happened in the solar system. Each planet cooked in a slightly different way, depending on how close it was to the sun. Near the sun, where it was hot, gases burned off and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, could survive. This is why only rocky planets formed close to the Sun. As a planet moves farther away from the Sun, it cooks in a different way. The type of planets that form depends on what's in the dust cloud. If a solar system forms from a cloud that doesn't contain enough material for rocky planets, it might only have gas giants. If you want rocky planets, you need a cloud full of metals and rocks. As the dust cloud cools, materials with high boiling point start to condense into solids, forming small mineral grains. These tiny pieces of rock and minerals are the beginnings of a new rocky world. Over time, they start sticking together. If you had one dust molecule and another dust molecule, they would collide and make a slightly bigger dust particle. This process continues, with dust particles gradually sticking together and growing larger. This process is called accretion. As the particles grow, they become rocks. Then rocks slam into other rocks, forming boulders. Boulders smash together, creating even larger boulders. Eventually, you get something big enough that its gravity becomes strong enough to pull more material toward it. Instead of just colliding with things to get bigger, the growing planet begins actively pulling material in. In the early solar system, there were likely about 100 young planets. Most of them didn't survive. If you look at the asteroid for Vesta in the asteroid belt, you can get an idea of how large a hard planet has to be before it can pull itself into a spherical shape. Vesta, at 329 miles across, isn't quite large enough to be a sphere. A planet needs to be at least 500 miles across to have enough gravity to crush itself into a sphere. If it's smaller, it stays irregular in shape. Every time a round baby planet crashes into something, it heats up more and more, until it starts to melt. Gravity then begins sorting the heavy materials from the lighter ones. The lighter materials float to the surface and form a crust, while the heavier metals sink to the center, forming a denser core. Finally, these young planets begin to look more like actual planets, but they must still survive a violent and destructive phase, a cruel time that determines which planets will live and which will die. After the Sun was formed, all 8 of our planets emerged from the same cloud of dust and gas. But they turned out to be very different. There was no specific plan for how each new planet would be created. While they followed the laws of physics and chemistry, much of what happened was simply a matter of luck. About 4.5 billion years ago, our Sun was surrounded by around 100 young planets. It turned into a demolition derby. Planets collided with each other, and most were destroyed. The early history of these planets was incredibly violent, with many collisions happening during the final stages of each planet's growth. As these collisions occurred, some planetesimals grew at the expense of others. These objects, which would eventually become planets, grew larger and larger. As they got bigger, they pulled in smaller planetesimals around them, causing a lot of space debris to hit the surface of the protoplanets. When it was all over, only 4 rocky planets were left. Due to events in their past, each planet turned out very different from the others. Mars is a frozen wasteland, Earth has flowing liquid water, Venus is full of volcanoes, and Mercury is small, barren, and extremely hot. Mercury, for example, likely experienced a massive collision. As a result, its thin crust and dense core suggest it may have once been a larger planet, but something hit it at an angle, stripping away its lighter crust and leaving only the dense center. Earth was also hit hard. Toward the end of its development, a massive object collided with Earth, tearing apart its mantle and sending pieces into orbit. These pieces eventually came together to form the Moon. Mars also seems to have experienced a significant impact. The northern hemisphere of Mars has a thinner crust than the southern hemisphere, and one theory suggests that a massive object hit Mars early in its history, blowing off much of its northern crust, which then accumulated in the south. These collisions had 2 major effects. They reduced the number of baby planets and delivered new materials to the survivors. If a collision involved a metallic object, those chunks would sink down to form the planet's core, while lighter or icy materials would float and become part of the crust. near the Sun, for rocky planets were nearly complete. They had solid iron cores, surrounded by layers of liquid iron and molten rock, with a crust on the surface. Even though these rocky planets were formed in the same way and from the same basic materials, each of them turned out very different in size, and with very different destinies. Space may appear empty, but it's not. It's full of matter expelled from the Sun. The Sun generates strong magnetic fields, which rise in massive loops above its surface. When these loops collide, a storm of hot, charged particles is flung into space. This is known as the solar wind. Astronauts in space can sense the solar wind, but only when they close their eyes. When you close your eyes, you might sometimes see a tiny flash. That flash is caused by an energetic particle passing through your head and interacting with the fluid in your eye. Astronauts see one of these flashes every few minutes. Solar wind could be deadly for astronauts if they were exposed to high levels of it. During the Apollo missions, there was a solar explosion between two moon landings that would have killed the astronauts if they had been there at that time. However, here on Earth, the solar wind doesn't pose much of a threat because we are protected by an invisible magnetic field generated by the Earth's core. Magnetic fields can be created through motion by converting the energy of motion into magnetic energy. This is exactly what happens deep inside the Earth. As the Earth spins, the hot, liquid metal inside it flows around the solid core, transforming its energy into a magnetic field that extends out from the poles. This magnetic field prevents the solar wind from entering the planet's atmosphere. If a planet has a magnetic field, it diverts the solar wind around the planet. Earth's magnetic field pushes the solar wind away, protecting the atmosphere and everything on the surface. Sometimes, large storms of solar radiation can disrupt the magnetic field, causing spectacular light displays known as auroras over the poles. Without a magnetic field, Earth's atmosphere and water would be blown away by the solar wind, leaving it dry and lifeless, much like Mars. Mars was formed in a similar way to Earth, but today it is cold, dry, and inactive. So, what caused such a drastic change between the two planets? In 2004, NASA sent two robots, the Spirit and Opportunity rovers, to Mars to explore its surface. They confirmed that Mars is a barren, dangerous desert with an atmosphere much thinner than Earth's. However, they also found evidence that water once existed on Mars. Mars wasn't always a dry, barren place. Strong evidence shows that water was once beneath the surface, rose to the top, and evaporated. In some areas, we can even see ripples in the ground, formed by flowing water. This suggests that water once flowed across the Martian surface, and where there was water, there was likely a thick atmosphere. But what changed? Mars, like Earth, had volcanoes in the past, meaning it once had a hot interior. Its core, composed of iron and surrounded by liquid metal, should have generated a magnetic field just like Earth. But Mars is smaller than Earth, meaning it lost heat more quickly. As the core cooled and solidified, the convection that drives the magnetic field stopped. Without the magnetic shield, the solar wind stripped away Mars' atmosphere, causing the water to evaporate. Mars turned into the cold, empty planet we see today. Mars, Earth, Venus, and Mercury, the rocky planets, all formed within 150 million miles of the Sun. But further out, about 4 times farther, the Sun shaped a different kind of planet. Here, gas giants like Jupiter, Saturn, Uranus, and Neptune formed. These massive planets have no solid surfaces and are made of gas, with thick atmospheres of hydrogen, helium, and methane. Astronomers have discovered over 400 new planets in other solar systems, and nearly all of them are large gas planets. Our solar system has 4 gas giants, all with thick atmospheres that extend tens of thousands of miles. These gas giants also have many moons, with Jupiter and Saturn each boasting over 60 moons. Additionally, the gas giants have rings. Saturn is the most famous for its striking ring system, but Jupiter, Uranus, and Neptune also have rings. Saturn's rings, though, are the most visible from a distance. From far away, Saturn's rings appear to be a single, flat disk, but in reality, they consist of thousands of smaller rings, each only a few miles wide. When the Cassini probe flew by, it discovered that billions of pieces of ice and space debris were moving within the rings at speeds of up to 50,000 miles per hour. These pieces of ice and rock constantly collide with one another. Some form small moons, while others break apart. However, they never grow larger because Saturn's immense gravity tears them apart. Scientists are just beginning to understand how these rings came to exist. One idea is that a comet collided with a moon, knocking it out of orbit and bringing it closer to Saturn. Saturn's gravity then ripped the moon to pieces, and all of that debris got trapped in the rings surrounding the planet. But the true mysteries of the gas giants lie deep within them, tens of thousands of miles below their clouds. This is where things get really strange, a place so extreme that it defies natural laws. Most of the new planets we've discovered orbiting distant stars are huge gas giants, much larger than Jupiter. But no one truly knows what happens inside gas giant planets, whether they are in our solar system or far away. We know that Jupiter's thick atmosphere extends down for about 40,000 miles, and we can see bands of gas moving at high speeds, causing violent storms on the surface. But what happens deep inside remains unknown. NASA sent the Galileo spacecraft on a 14-year journey to Jupiter to investigate. On December 7, 1995, Galileo deployed a probe into Jupiter's atmosphere at a speed of 160,000 miles per hour. As it descended through the dense air, its parachute slowed it down. The probe observed lightning in the clouds and winds reaching speeds of 450 miles per hour. For 58 minutes, it transmitted data back to Earth. What happened to the Galileo probe? It didn't hit a solid surface, it just kept falling into Jupiter's environment, where the pressure continued to rise. As it descended, it recorded pressures 23 times higher than those on Earth and temperatures over 300 degrees Fahrenheit hotter. In the deep environment of a gas giant, as you descend further into the hydrogen soup, even without a solid surface, the material becomes incredibly heavy. Eventually, the probe was crushed by the immense pressure after descending just 124 miles. Although it didn't survive for long, it gave scientists valuable insights into Jupiter's interior, but the planet's dark core remains a mystery. Like some rocky planets, gas giants also have magnetic fields. Jupiter's magnetic field is 20,000 times stronger than Earth's, extending all the way to Saturn, more than 400 million miles away. Just like on Earth, Jupiter's magnetic field deflects the solar wind, protecting its atmosphere. But when scientists studied Jupiter's magnetic field, they discovered that it also affects the planet's moons. The volcanic moon Io, which orbits just 217,000 miles from Jupiter, spews a ton of gas and dust into space every second through its volcanoes. This becomes even more intense due to Jupiter's magnetic field, which creates powerful radiation belts, making the region around Jupiter highly active. In fact, if you point a radio antenna at Jupiter, you can hear how the planet's magnetic field interacts with its surroundings. Jupiter and Saturn are capable of creating auroras without the solar wind. Their enormous magnetic fields generate these auroras, showing that even gas giants have magnetic fields. But how do gas giants create magnetic fields? On Earth, this is done by a hot, liquid metal that spins around the planet's solid iron core. Gas giants likely have a similar mechanism, but they don't have hot iron cores. Instead, they formed around frozen cores of dust and ice. So, we really don't know what's going on inside them. We don't know what makes up the deepest parts of Jupiter's interior. It's possible that Jupiter has a solid core at its center, or it might still be liquid. We may never know for sure, as no probe could ever travel the 44,000 miles to reach the planet's center. The Galileo spacecraft was destroyed before it could reach the core of Jupiter. Gravity and heat shape how planets evolve, from their inner cores to their outer atmospheres. These are the great creative forces behind planet formation. However, there's one more key ingredient that has a big impact on how planets turn out, and that is water. Planets may look like they are static and unchanging, but they are constantly evolving. One planet in our solar system lost its atmosphere and turned into a desert. Another planet became too hot and transformed into a hellish place. Even Earth has changed over time, and water played a major role in that transformation. When you look at Earth from space, you can see a lot of water, which is why it's called the blue planet. It might seem like Earth is very wet, but in reality, only 0.006% of Earth's mass is water. Some of that water is in the oceans, and some is trapped in the mantle. In truth, Earth is a relatively dry rock. All the inner rocky planets formed close to the Sun, so they started off dry. Any water they initially had evaporated or was blown away during the violent collisions that helped form the planets. If there had been water on Earth during those early collisions, it would have evaporated and disappeared. So, where did the water on Earth come from? When we look at Jupiter, Saturn, Uranus, and Neptune, we see they have a lot of water trapped inside them. Their moons also contain vast amounts of water. But how did some of that water end up on Earth? The answer is likely that some asteroids and comets, which were far enough from the Sun to retain their water, made their way into the inner solar system. Millions of these watery asteroids and comets crashed into Earth over time, gradually depositing the water that now covers most of the planet. Without this surface water, life wouldn't have existed. But what if Earth had too much water? The oceans would be much deeper, covering the continents and even Mount Everest. It's likely that the exact amount of water Earth has is what made it possible for humans to evolve into a technological species. Around 4 billion years ago, a bombardment of comets and asteroids brought just the right amount of water to Earth, shaping the world we know today. It's possible that the same process is happening somewhere else in the universe right now. There is a lot of water out there, that much is certain. The most common atom in the universe is hydrogen, and oxygen is also one of the most common elements. Together, they form H2O, making water a very common molecule. This means water is widespread throughout the universe, and we're also discovering that planets are common too. However, we haven't yet found another planet where water is liquid. More than 400 new planets have been discovered by scientists, but none of them are quite like Earth. What we haven't found yet is a planet around another star that is the same size, mass, and chemical composition as Earth. Finding such a planet remains an extraordinary goal for humanity, a kind of holy grail. But we will keep looking. Our galaxy alone contains around 200 billion stars, and up to 40 billion of them could have their own planets. We are entering what will be known as the golden age of planetary exploration. In the future, we will begin to truly understand how different things are out there. The laws of physics and chemistry tell us how planets form. Many scientists believe it's only a matter of time before we find another planet like Earth, one that formed from the same materials, in the right place, with the right amount of water. One thing is certain, there are billions of planets out there, waiting to be discovered.